Hello everyone, I'm Martin, a PhD student at the University of Luxembourg, and I'm very pleased to introduce you today our work in our paper called Search-Based Adversarial Testing and Improvement of Constrained Credit Scoring Systems. First of all, I would like to thank my co-authors, Salah, Maxime, Mike and Yves from the University of Luxembourg, and André and Anne from BGL BNP Paribas, our industrial partner. This collaborative work with the Data Science Lab of BGL aimed to answer a real case issue that the bank is facing. We also worked with their expert to provide a working and efficient solution to this problem. Today, banking is evolving to offer new services to clients with more automation and personalization. How can we ensure that the transactions that are processed automatically are legit? Indeed, when a human operator is involved, let's say to authorize or deny a transaction, the operator can evaluate all the elements of the transaction, taking into account the customer behavior and habit, and use forecasting and risk evaluation tools to make the final decision. After this due diligence, the operator can allow the transaction or deny it. Error can occur and the operator could indeed make a mistake. However, the full process is under human supervision. Our partner has implemented machine learning approaches in multiple of their systems: credit scoring, money laundering, fraud detection, etc. Our paper focuses on one of them, the overdraft system that can be seen as a credit scoring system. The two main assets of this system is that we can work with the model and data that are actually used in production and be close to real case condition. Secondly, credit scoring dataset and model are available in the literature and people could reproduce and reuse our approaches with minimal changes. The machine learning system is trained using previous human decisions. The dataset is therefore large and it requires dedicated resources for the future engineering and model training. The decision is a single machine learning prediction that takes as an input all the information of the requested transaction and of the associated client. The acceptance should reflect the human operator reasoning. In the case of our partner, rejected transactions are evaluated later by a human operator. The operator can confirm the rejection or cancel the rejection and process the transaction. In this case, the new decision is added to the dataset and the model training will include this new case. However, if the system accepted a transaction that should have been rejected, the bank supports the loss and the right decision is appended to the training. But what if the clients willingly fool the system and create so-called adversarial attacks against the machine learning system? Adversarial attacks in machine learning is a process in which we introduce a small perturbation to an input in order to create a large change in output. This picture is a famous example from computer vision. Here, a small adversarial perturbation is added to an original image of a panda to create an adversarial counterpart. It still looks like a panda to a human, but it is classified as a gibbon with very high confidence by the attacked model. In our case, away from computer vision, it's a bit more complex. The input is not only the new transaction, but also the current state of the client. The current state includes, for instance, its asset and balance, and both need to be realistic and achievable. If the attacker wants to flip a transaction from being rejected to being accepted, the attacker will need to start from a valid state. We start from an initial state and a rejected transaction that we add a small adversarial perturbation that will switch this rejected transaction to an accepted one. This accepted transaction will need to validate several constraints. It needs to be realistic, it needs to be close to the rejected transaction, the original transaction, and also the transaction amount should be large. The achievable constraint means that the client should be able to reach the adversarial state using 6 successive valid transactions. The realistic constraint means that the domain-specific constraint should be respected. Here we consider a gray box threat model. It means that the constraint can be evaluated by the attacker, but the model internal parameters are not. The first preliminary research question that we introduce is to know if the feature space attack, that is the classical attacks in machine learning security, will suffice to fool our partner's credit scoring system. So we will see that it's not. The following research questions that we are interested in is if we can find a set of initial state and adversarial transaction where an adversarial attacks would work. We will see that indeed it's possible. Therefore, we are interested into investigating the robustification of our partner's model. Can we improve the random forest to resist our attack? We will show that indeed we can train a new and more robust model. The credit scoring system is built on top of feature engineering that make use of data across multiple accounts and clients collected for a long period of time. Manually uncrafted rules and transformation are used, and sanity checks against local and global constraints are performed. In the end, we have almost 50 features after consolidation, 275,000 transactions for training, and 125,000 transactions for testing. Then, a random forest classifier is built using this dataset. Cross-validation is used for hyperparameter tuning, and regular training is performed to fight against concept drift. Then the model is deployed, and it's composed of 500 estimators per ensemble, and we end up with a 0.99 terrain AUC and 0.88 test AUC on random split. The first part of our problem formulation is a standard adversarial example search. Here we want to find a perturbation in feature space. The objective is to have the smallest perturbation that changes the prediction of the new transaction from a reject to an accept. The p distance here between the perturbed input and an initial one is a good indication of the effort required to generate the adversarial example. The challenge here resides in the second part of our problem formulation, that is the constraint of our application. Constraints are of three types. First, some feature cannot be perturbed. For instance, the level of risk associated to a customer is under the control of a bank and cannot be changed by the consumer itself. We define, therefore, a set of mutable features. Secondly, some features are bounded. They have a minimum and a maximum values. Bounds are defined per feature as they are not all equal. Most come from the feature space, but we also added the constraint that the amount must be higher than 1,000 currency units for relevancy. Third, some features are related to others. We defined a set of equations that ensure that the perturbed point in feature space could correspond to a valid transaction and initial state. For example, the perturbed transaction has to remain an overdraft, that is, that the transaction amount must remain above the current balance of the customer account. Here you can see some examples of constraint or relation between features. For confidentiality purposes, the constraint presented here came from another open dataset. But here you can see something important is that we don't necessarily have linear relationship between features. We start by our preliminary research question. How effective are state-of-the-art attacks to fool the credit scoring system? We applied PGD and CW2 that are gradient-based attacks on a surrogate model. Paper notes attack is applied iteratively to a subset of trees from the forest. Both types of attacks fail to fool the system while being realistic. Our intuition here is to use evolution to attack the credit scoring system. We call our attack co-eva2. We consider 4 success criteria for our evolutionary algorithm. The first one is to satisfy the domain constraints. The second one is to cause misclassification. The third one is to satisfy the first and the second ones at the same time. And the fourth one is to satisfy the third with the relevant amount in overdraft. Here, we consider a threshold in currency units above which the attack is considered relevant. We make use of multi-objective evolutionary algorithm for our attack. Our multi-objective fitness function is composed of 3 domain objectives plus a constraint. All of them are to be minimized. All objectives are normalized between 0 and 1. The weights for each objective are selected with the domain expert to reflect the priority and the importance of the objective. The first objective, here noted F1, is to flip the predicted class. A rejected transaction is predicted as 1, therefore flipping the class implies to decrease the probability of the class being rejected. The second objective, noted F2, aimed to restrict the perturbation to the original transaction, hence limiting the L2 distance between the original and the adversarial transaction. F3, the third objective, aimed to maximize the amount of the transaction being accepted. This is important for the attacker because the attacker wants to maximize the amount in overdraft. The last objective, F4, is the mean of constraint violation. We include the constraint violation as a soft objective to be minimized. All constraints are given the same weight. Soft constraint evaluation allows the exploration of future population even if the parent population may still break some constraint. We start from 4,000 initial states randomly sampled from the test dataset. And we give to the evolutionary algorithm 10,000 evolution generation budget. If random search succeeds in generating misclassified examples, they don't satisfy the domain constraint. However, co-eva2 is able to generate adversarial examples that both are misclassified and satisfy the constraint 17.2% of the time. If we remove the transaction with a small overdraft amount, we are able to generate realistic and significant transaction in overdraft 8.45% of the time. Note that we need all the fitness function objective to ensure the success of the attack. We can see in the lower graph that the constraints are resolved after 100 generation. In the upper one, we can note that the overdraft objective reaches its maximum within 200 generation. In the end, we show that we can find a set of initial state and rejected transaction, such as an adversarial attack work. The second research question that we investigated is if we can improve our partner's model to resist problem space attacks. Here, we want to find adversarial example and then add it to the train test to see if we can find a better model, a model that is more resistant, more robust to new attacks. To do so, we start with 4,000 samples from the test set. We transform them into adversarial example using co-eva2. Then we add them to the train set. We train a new random forest using this augmented dataset. Following that, we use 4,000 other samples from the test set. We again use co-eva2 to craft new adversarial examples against the newly trained and improved model. We observe that we were not able to find any adversarial examples that satisfy our criteria. Therefore, we conclude that we were able to improve our partner's model to resist to some attacks. We left different directions for future work. First of all, initial states are randomly sampled and not searched. Maybe we can optimize both the state and the attack. Second of all, objectives weight are defined by domain expert. We can probably apply search and adaptive weights or Pareto evolution to end up to better solutions, better result. Also, third, we tried robustification through adversarial training, but we would be able to explore other defensive mechanisms to see if other defense can lead to more robust model. To summarize, we show first that current adversarial attacks fail to attack a real industrial system because of domain constraint. Second of all, we show that an evolutionary algorithm that we call co-EVA2 is able to find adversarial examples that succeed in attacking the industrial system because it respects domain constraint, misclassified, and maximize the overdraft amount. In the end, we show that we can use this adversarial example as a strong defense mechanism if we add them to the training set and if we perform adversarial training. More details can be found in our paper available in the link in the slide. Also, we made available our code in GitHub, and we also are available for questions after the presentation.